Alright, so let's go through these Newton's second law practice problems. Number one, a rightward force of 302 newtons. I'm going to draw that in as I go. 302 newtons is applied to a 28.6 kilogram crate. So mass is 28.6 kilograms. To accelerate it across the floor. The friction between the crate and the floor is 215 newtons. But another force going backwards, friction of 215 newtons. Determine the acceleration of the crate. Alright, so I have 302 newtons pushing it forward, 215 newtons of friction pushing it back. Of course, I have the weight and normal force, so they don't affect this problem. I'm going to leave them in there just so I know those forces are there. First things first, I need the net force. Now, since the normal force and the weight would cancel out, not accelerating through the floor, we have just the 302 newtons minus the 215 newtons, and that gives me 87 newtons. Alright, so that's my net force. That's the second step. I want to know how much it's accelerating. So acceleration, now I apply Newton's second law. So net force divided by the mass. So that's 87 newtons divided by 28.6 kilograms. My acceleration is 3.04. We're on that 3.0. I'll see the tenths for this round. Meters per second per second. Number two, during a football workout, two linemen are pushing the coach on a sled. The combined mass of the sled and the coach is 300 kilograms. So let's record that, 300 kilograms, and that's an O, not a 6. The friction between the sled and the grass is 2,400 newtons. So I have a force pushing backwards, and I'm going to put that to the left, of 2,400 newtons. Alright, the sled accelerates at a rate of 0.580 meters per second per second. So I know the acceleration of the whole system in this case. Meters per second, which means there's some force pushing it forward. I don't know what that is. I'm just going to call that F right now. Determine the force applied by the sled by both linemen. Alright, so on this sled, again, it's on the ground, so I still have weight, and I still have a normal force. I know the friction, but I don't know what force they're applying. The process is the same, though. I have my free body diagram. So my net force, in this case, would be whatever force I'm pushing with, minus the force of friction. So that would be whatever force I'm pushing with minus 2,400 newtons. Now I can't get much farther than that because I don't know what the actual net force is. That's okay. Third step, apply Newton's second law. So net force is equal to mass times acceleration. That's the same net force that we figured out over here. So the applied force minus 2,400 newtons, because that was the net force I found over here, is equal to mass times acceleration. So I'll plug in all the things I do know. Minus 2,400 newtons equals, the mass was 300 kilograms, and the acceleration was 0.58. And now we do some math. And that gives me 174 for the actual net force. Now that net force was the force I'm pushing minus the friction, so I'm going to add that friction back to both sides, plus 2,400, plus 2,400, and that gives me an applied force of 2,574 newtons. Now, could I have solved for my net force first with the mass and acceleration, and then plugged that net force in over here? Yeah, sure, nothing wrong with that. It's just all algebra. The order you do it doesn't matter in this case. Number three, we have a 6,580 Newton upward tension force. Alright, so I have a force pulling up here, 6,580 newtons is my tension. Exerted on a 521 kilogram downward moving freight elevator. Alright, so we have mg's, the weight pulling down. My m, in this case, the mass, was 521 kilograms. Determine the acceleration of that elevator. Well, I got to figure out what that weight is. There's no force pushing along the sides here, since it's an elevator going up and down. So let's figure out what that weight, mg, that force due to gravity, would be 521. I'm going to use acceleration due to gravity of 10 meters per second, just to make things easier on ourselves right now. So 5,210 newtons. All right, and luckily I drew that proportionally well, because that is actually less than the tension pulling on it. So if that's my weight, that's my mg, I'll throw that in my diagram, 5,210 newtons. So got my free body diagram. Now, next step is the net force. My net force would be the tension that's pulling up, that's 6,580, minus the weight that's pulling down, so tension, T, minus mg. You want to do that first. So minus the 5,210 gives me 1,370 newtons as a net force. And it asked me to look for the acceleration. Alright, so acceleration, that is the net force divided by the mass, Newton's second law. So, 1,370 newtons divided by 521 kilograms gives me an acceleration of, pause, about 2.63 meters per second, or about 2.6 meters per second. On to number 4, 4A. We have a basketball star exerting a force of 3,225 newtons on average upon the gym floor in order to accelerate his 76.5 kilogram body upward. So determine the acceleration of the player. Alright, so here's our player. We have mg pulling down. He's exerting a force upwards. So that's the force he's exerting upwards. That force that's being exerted upwards is 3,225 newtons. And his mass was, read this again, 76.5. So 76.5 kilograms times 10 meters per second gives me a weight of 765 newtons. Alright, so now I do my net force. I have my free body diagram. Net force would be the force that he's pushing up minus his weight pulling down, 765, which gives me 2,460 newtons. Alright, so that's my net force, and be on him upwards, because he's accelerating himself upwards. We want to determine the acceleration, though, so onto our trusty second law, net force divided by mass. So that's 2,460 newtons divided by 76.5 kilograms gives us about 32.2 meters per second of acceleration. Alright, so that's part A. Part B asks us to determine the final speed of the player. So VF, that part A, I'll separate these. VF, if the force endures for a time of 0.15 seconds. So I have a final velocity, I have a time 0.15 seconds. I know the initial velocity would start off as 0, since he's jumping, I can assume that, and I have the acceleration from previous, so that final velocity, I go back to my linear motion, equals initial velocity plus acceleration times time. So initial velocity of 0 plus 32.2 times my time, 0.15 seconds, and that would be 4.83 meters per second. So that's how fast he's going once he leaves the ground, once he's done pushing off. And that would be part B. Number 5. At the end of a giant drop free fall ride like Scream at Six Flags, riders experiences a large upward normal force to bring their falling bodies to a stop. Alright, so we have a large normal force, we have still some mg pulling down some weight from their weight. Determine the normal force value required to accelerate a 52.1 kilogram physics student. So that's 52.1 kilograms times 10 meters per second. That physics student weighs 521 newtons. All right. With an upward acceleration of, giving us an acceleration of 27.4 meters per second. Right at the end there, slowing them down. All right, so we need a net force, and that's going to be the normal force, which is pulling up, minus the weight, so minus mg, which we know. We also know Newton's second law, the net force is also equal to mass times acceleration. So I could plug this in like I did for, I believe it was number 2 or 3, one of those, but I'm going to do this one the other way. So I have mass of 52.1 kilograms, and then I have an acceleration of 27.4 meters per second. I'm going to solve for the net force first, and then plug that back into my equation on the left. Alright, so multiplying those, I have 1,427.54, and I'm not going to round anything yet. I want to get to all the way to the end first. Alright, so that's my net force. So I'm going to go over here and say, okay, my net force is 1427.54 equal to whatever the normal force is, which is what I'm trying to figure out, times our weight, which I calculated up here, so that's 521 newtons. That's being subtracted, so I'm going to add that to both sides. 521 plus 521 gives me a normal force equal to, add that on, 1,948 newtons and a half, 0.54, around that. Alright, and that is our normal force. That's what we want. Alright, so number 6, a hockey player accelerates a puck which has a mass of 0.167 kilograms from rest to a velocity of, so from rest means initial velocity of 0 to a velocity of 50 meters per second, so that's a final velocity of 50 meters per second in 0.0121 seconds. So that gives me a time of 0.0121 seconds. Determine the acceleration of the puck, neglect friction. Alright, so without friction, we need to go back to our, well, no forces involved in this case. It gives us a change in velocity and a time, which is what we need for acceleration. Change in velocity over time. Back to our linear motion stuff. So 50 meters per second minus 0, that's what we started at, and a time of 0.0121 seconds, which would give me an acceleration of 4,132.2 meters per second. So that is quick. Well, it happens fast, though. Alright, then we want to 6b, find the force, which was the first one. Alright, 6b is find the force applied by the hockey stick to the puck. Still neglect friction. So in this case, if this puck's on the ground, it probably has a weight, it probably has a normal force, and it's just the force applied, and that's what I want, no friction. So in this case, the net force is, well, just the force applied, which is all I want. So F equals mass times acceleration. My net force is that force applied. So my mass was 0.167 kilograms. My acceleration was 4,132.2 meters per second. And if I still had that full number in my calculator, I want to keep that in there so I don't have to round in the middle of a problem. I won't. And I do have that still in there, so I'm going to multiply by 0.167, and that gives me 690.1, we'll say, in newtons. That's the force applied to accelerate that puck up to that speed. Number 7, moving right along, we have a falling skydiver. It's accelerating in the downward direction at 3.29 meters per second. So we're accelerating 3.29 meters per second downward. Alright, the mass of the skydiver, including the parachute gears, is 67.2 kilograms. So we have a mass of 67.2 kilograms. Determine the air resistance force on the skydiver and the accompanying parachutes for the whole system. Alright, so there's my skydiver, and the forces on that skydiver would be the weight pulling him downward. Now it does say he's accelerating downward, so whatever force is pulling up, whatever air resistance from him in a chute, that, I'll call that F air, because I guess it is air resistance, would be less than that weight since he's accelerating downward. That must mean his weight is winning. That's what we want to find, that's what we don't know. So how do we do that? The same way we've done all of these problems. Set up our net force. Now we need to make sure we think about direction. The air resistance is pulling up, so I'm going to keep that positive, and the weight is pulling down, so I want to make sure that goes in as negative, coming downward there. Now I don't know what the net force is, I know what the weight is. Let's also set up our second law equation over here. Net force is equal to the mass times the acceleration. So a net force, that we can actually solve. Mass, 67.2 kilograms. The acceleration of 3.29 meters per second. Now, we did say that was downward, and I want to make sure this takes care of that here. And we say it's a negative 3.29 meters per second. So, our net force then would be 221.088, and I'm not going to round yet because we're not done with the problem. Alright, so we have a net force, and that would then be negative. Why is it negative? It's in the downward direction. So that's what tells us that weight is winning. It's accelerating downwards. Alright, let's plug that back into our original equation here for net force. So we have negative 221.088 newtons is equal to the air resistance that's pulling him upward minus our mass, 67.2 kilograms, times acceleration due to gravity, 10 meters per second. Alright, and now we have air resistance minus his weight, 672 newtons. That's pulling downwards. 221.088 over here on the left. We add that 672 to both sides, plus 672, and the air resistance would come out to be, alright, that would give you 450, oops, my pencil tool back here, 450.9 newtons. Again, because that 221 net force was negative, that was downwards, because the weight was winning. Alright, number 8. A 67.2 kilogram falling skydiver opens his parachute and instantly slows down at a rate of 7.2 meters per second. Alright, let's keep track of that. 67.2 kilograms, same person as the last one. Opens his parachute, slows down at a rate of, that gives me an acceleration, 7.2 meters per second. Determine the air resistance force on the skydiver. Alright, so there's our skydiver. We have weight pulling him down and a air resistance pulling him up from the parachute. If he's accelerating, or if he's falling and he's slowing down, that tells us he's actually accelerating upwards, because he was falling and speeding up and now he's slowing down. So that's acceleration working in the opposite direction here. So my net force, I'm going to write as the air resistance minus the weight, because the weight's pulling him down, air resistance is pulling him up. I'm going to keep downward as the negative direction. And I'm also going to set up my second law over here. Net force equals mass times acceleration. 67.2 kilograms, acceleration of 7.2 meters per second, which gives me a net force of 483.84 newtons. That would be the net force. And if he's falling and slowing down, that net force is still positive, upward, because our acceleration was positive and upward. Alright, so we come back over here to our net force equation and say, alright, 483.84 newtons is equal to our air resistance, which we don't know, minus our weight, which we haven't calculated yet, but we can do that right now, 672 kilograms times, if we're talking weight, we're talking acceleration due to gravity. Now notice I don't put the acceleration due to gravity in there as negative, because I've already taken care of that over here. I'm already subtracting the weight. I'm already taking care of that direction. If you wanted to put the acceleration in as negative, because you want that acceleration pointed downwards, then you can't do that twice. I'd have to say I'd add that force in with a negative acceleration. But I'm not going to do that here. I like to take care of that once right in the beginning. So we have the air resistance minus a weight of 672 newtons. That's what's pulling him downward. Carry through that net force, newtons, since I'm subtracting 672. I'm going to add 672 to both sides, which is the weight, which gives me an air resistance of 1,155.8 newtons. And that would be my air resistance.